In this lesson, we're going to discuss software-defined networking, or SDN. Software-defined networking is revolutionizing our network architectures, and it is critical to the functioning of the cloud at scale. At its most basic level, software-defined networking allows us to use software to replace traditional network devices. But it's a little bit more complicated than that, so we're going to spend a little time in this lesson discussing how it works. Software-defined network, or SDN, is defined as an approach to networking that uses software-based controllers or application programming interfaces, APIs, to communicate with the underlying hardware infrastructure and direct traffic on the network. It is a critical aspect of cloud computing, as it allows organizations to more easily manage and control their network traffic, which can improve scalability, security, and overall network performance. I should mention that software-defined networks are part of a larger concept known as infrastructure as code, or IAC. Infrastructure as code includes the provisioning of architecture in which deployment of resources is performed by scripted automation and orchestration. SDNs are not the only type of infrastructure as a code, but with SDNs, it will be impossible to use IAC with networking equipment and devices. With IAC, the infrastructure could be a network device such as an SDN, or servers, databases, and other virtualized computing instances. To better understand software-defined networking, you first need to understand the three portions of a typical network architecture, and that's going to be the control plane, the data plane, and the management plane. The control plane is responsible for carrying the traffic that provides the signals to and from a router, such as those using information sharing and building routing tables. The control plane makes decisions about how traffic should be prioritized, secured, and where it should be switched to in the network. If you think about a traditional router or switch, or a quality of service device, these all operate at the control plane layer. The data plane is the second plane, and this data plane is used to carry user traffic on the network. This is often called the forwarding plane as well. The data plane is where the bulk of our network traffic resides, and this is where the actual switching and routing of the traffic and imposition of access control lists, or ACLs, are implemented to provide some level of security. To make this a bit easier to understand, remember that the control plane makes all of the decisions for how the data is going to be moved, but it's the data plane that's actually moving the data around for you in the network. Therefore, as you can imagine, these two planes work very closely together. Third plane is the management plane. The management plane is used to administer the routers and switches inside the network, and it is used to monitor traffic conditions and the status of the network. Basically, the management plane provides us with the oversight of the network and allows us to make configuration changes to make sure that things are working the way they should be. Now, in a traditional or conventional network, these different planes all exist in a physical piece of hardware that implements these functions through firmware in that device, like a router or a switch. But with software-defined networking, these functions are moved out of the physical devices and their firmware. Instead, these functions are incorporated into a virtualized device or decoupled device that focuses on a single plane's function at a time using APIs provided by the vendors to communicate between those three planes. To set up a software-defined network, your organization will use a SDN application to define the policy decisions. This occurs at the management plane, and those rules and policies are going to be deployed and operated within the control plane of the different devices. Of course, the data plane will still be used to move the traffic across the network. Using an SDN has some advantages over conventional networks, such as having the ability to mix and match products from different vendors because they're all using a common API call to create the needed functionality. Software-defined networks also provide organizations with increased choices in their network development, adding to the speed and agility in which you can establish a network. This also adds the ability to add increased layers of automation and policy management in our organization's network functions by easily using programming to automate all of this stuff. But the best benefit of an SDN is that it can allow for a fully automated deployment of a network within the cloud too. By using SDN, you can have the ability to provision all of your network links, your applications, and even all your servers all automatically through the use of orchestration. So if you're running servers in the cloud and need to horizontally or vertically scale up to create more capacity, the system can actually detect that and automatically spin up additional resources for you and then add them to that SDN network. Because of all these automated capabilities and scalability, SDNs are critical when you're dealing with high velocity or high availability architectures, or if you're doing a lot of things inside of the disaster recovery space. Also, because everything is software, you can make it easy for yourself to collect security data across the entire network as well, because everything is just ones and zeros. This allows your security team to more easily detect the different traffic patterns in your network, and if they start deviating from normal baselines, you can also detect that as well. Software-defined networks do have some disadvantages as well. For instance, if we lose connectivity to the SDN controller, then the entire network can go down and we could lose our ability to control it. Also, the use of centralized controllers and SDNs creates a real target for attackers to focus on, because they could cripple our entire network just by taking over that singular controller. So you need to ensure that all the proper steps are taken to make sure that the system is hardened and protected so that software-defined network controller is less vulnerable to attack. When it comes to software-defined networks, there are three main types: Open SDN, Hybrid SDN, and SDN overlay. The first is Open SDN. Open SDN is an open source variant of software-defined networking that relies on open source technology like OpenFlow, OpFlex, and OpenStack to operate. The second is Hybrid SDN. Hybrid SDN is a network that employs traditional and SDN protocols to operate itself. This allows the network to use open SDN technologies like OpenFlow as well as traditional protocols used in physical network devices. The third SDN is SDN overlay. SDN overlay is a method of using software to create layers of network abstraction that can be used to run multiple separate and discrete virtualized network layers on top of your physical network. By using SDN overlay, you can create virtual connections between different endpoints and provide additional security benefits using it. Now, don't get worried. For the exam, you don't have to be an expert in Open SDN, Hybrid SDN, or SDN overlay. From a security standpoint, using the SDN can add additional security, and it even allows you to implement isolation in your network. For example, to add additional security such as implementing zero trust, you may use SDN overlay to securely create logical peer-to-peer connections across physical network devices using these additional layers of abstraction. This is a great use of SDN to increase the security of your network, and it would be very hard to replicate without orchestration and the automation provided to us through the use of software-defined networking.